let's welcome you to our academy and welcome to today's video on AVL trees and node insertion. If you are studying data structures or preparing for technical interviews, understanding AVL trees is absolutely essential. Today, we are going to dive deep into what AVL trees are, how they maintain balance, and most importantly, how insertion operations work and trigger the rotations that keep these trees balanced. By the end of this video, you have a solid understanding of AVL tree fundamentals, the balance factor concept, and use serial examples of how insertions trigger rotations. So, let's get started. What is an AVL tree? First, let's establish what an AVL tree actually is. AVL stands for Adelson, Wilczek, and Landis, named after the two Soviet mathematicians who invented this data structure in 1962. An AVL tree is self-balancing binary search tree, and that's the key point. It's self-balancing. Now, you might be wondering, why do we need a self-balancing tree? Well, in regular binary search tree, if you insert nodes in a sorted order, you end up with essentially a linked list. For example, if you insert 1, 2, 3, 4, 5 in that order, your tree degenerates into linear structure. That's terrible for performance. AVL trees solve this problem by automatically rebalancing themselves after every insertion or deletion operation. This ensures that the tree remains approximately balanced, guaranteeing that operations like search, insertion, and deletion. The key property of AVL tree is this. For every node in the tree, the heights of its left and right subtrees can differ by at most 1. This is a strict constraint, and it's what makes AVL trees so efficient. So now let's talk about the balance factor, because this is the heart of how AVL trees maintain their balance. The balance factor of a node is simply the difference between the height of its left subtree and the height of its right subtree. We calculate it as shown in the slide. Balance factor is equals to the left height subtraction from the right height. In an AVL tree, the balance factor of every node must be -1, 0, or 1. Let me break down what each of these means. A balance factor of 0 means both subtrees have the same height, perfectly balanced. A balance factor of 1 means the left subtree is one level taller than the right. Is still acceptable. A balance factor of -1 means the right subtree is one level taller than the left. Also acceptable. If a node ever has a balance factor of 2 or -2, that's when we have an imbalance. And that's when we need to perform rotations to restore balance. Think of it like a scale. If one side gets too heavy, more than one level difference, we need to rebalance it. The balance factor is our way of measuring that heaviness. So, now let's talk about how insertion operations can cause imbalance. When you insert a new node into an AVL tree, you first perform a standard binary search tree insertion. You start at the root, compare values, and traverse left or right until you find the appropriate spot for the new node. However, this insertion can affect the heights of nodes along the path from root down to where we inserted. As we insert and then backtrack up the tree, we need to update the height of each ancestor node and check its balance factor. Here's where problems can occur. Adding a new node might increase the height of a subtree and that cause an ancestor node's balance factor to be 2 or minus 2. When this happens, we need 4 possible cases of imbalance. Left case. The insertion happened in the left subtree of the left child. Right case. The insertion happened in the right subtree of the right child. Left case. The insertion happened in the right subtree of the left child. Right-left case. The insertion happened in the left subtree of the right child. Each of these cases require a specific type of rotation or combination of rotations to restore balance. The first 2 cases are simpler and require single rotations, while the last 2 cases require double rotations. Now we come to the most important part, the rotations themselves. Rotations are structural modifications that reorganize nodes while preserving the binary search tree property. Let me explain each type. Right rotation. When we have a left-left imbalance, meaning the left subtree of the left child is causing the problem, we perform a right rotation. Imagine the imbalance node rotating clockwise. Its left child becomes the new root of the subtree. The original node becomes the right child and we carefully rearrange the middle subtree. As for the left rotation, this is the mirror image. When we have a right imbalance, we rotate the node counterclockwise. The right child becomes the new root. The original node becomes the left child. And again, we rearrange the middle subtree appropriately. So we have double rotations of left-right rotation and right-left rotation. Left-right rotation. This is a double rotation. First, we need to perform a left rotation on the left side, converting it into a left-left case. Then we perform a right rotation on the original imbalanced node. Think of it as a 2-step process to untangle a more complex imbalance. Now we have right-left rotation, another double rotation, but in the opposite direction. We first do the right rotation on the right child, converting it to a right case. Then we perform a left rotation on the right node. The beauty of this rotation is that they are local operations. They only affect small portions of the tree and they guarantee to restore balance while maintaining all the best properties. So let's walk through concrete examples that show how an insertion triggers a rotation. This will be a tie everything together. Suppose we have an AVL tree with nodes 10, 5 and 15. The tree is balanced with 10 as the root, 5 as the left child and 15 as the right child. All balance factors are 0. Now, let's insert the value 3. So 3 is less than 10. So we go left to the right, left to the node 5. 3 is less than 5. So we insert 3 as the left child of 5. After this insertion, we can update heights going back up to the tree. Node 5 has a left subtree of height 1 and a right subtree of height 0, giving it a balance factor of 1. That's fine. But now look at node 10. Its left subtree has height 2 while its right subtree has height 1. The balance factor of 10 is now 2. We have an imbalance. Specifically, this is a left-left case because the insertion happens in the left subtree of the left child. So, we need to perform a right rotation at node 10. Here's what happened during the right rotation. Node 5 becomes the new root of this subtree. Node 10 becomes the right child of 5. Node 15 remains as the right child of 10. Node 3 remains as the left child of 5. After this rotation, let's verify the imbalance. Node 3 has a balance factor of 0. Node 15 has a balance factor of 0. Node 10 now has both children at height 1. So let its balance factor is 0. Node 5 has a left subtree of height 10 and a right subtree of height 2, giving it a balance factor of -1. Everything is balanced again. To summarize what we have covered today, AVL trees are self-balancing binary search trees that maintain the balancing performance for all major operations. They use the balance factor, the difference in heights between left and right subtrees, to detect imbalances. When an insertion causes a node's balance factor to reach 2 or -2, we apply one of the 4 rotation patterns to restore imbalance. Right rotation for left-left cases, left rotation for right-right cases, and double rotations for left-right and right-left cases. The key takeaway is that AVL trees automatically maintain the efficiency through these local restructuring operations. While they require more overhead than simple binary search trees, this cost is worth it for the guaranteed performance they provide. So thank you guys for watching. If you found this helpful, please like and subscribe for more data structures content. And I'll do my best to continue these videos and meet you guys in the next videos. Thank you and see you guys in the next video.